and it doesn't matter which way it goes. That's not to fit on the table, but it goes in a circle on the table. And then you have the, what I'm going to call profile. So this cross-sectional view. You have your table with your thing and a string. And then drop down to the weights below. All right, so this is kind of the question that we have. When you're looking at this, right, you have two boxes. You have box 1 and box 2. So this is, I'll call it box 1 and box 2. That's box 1 up there, right? And what we're looking at here is if we do the free body diagram for box 1, we have the force of tension going towards the middle, normal force and gravity. Maddie, can you read that back there, or is that too small?
Yeah, I can read that.
You're good? Jackson, you're good? Olivia, can you read that? Let me know if you can. And box 2, you have the force of tension and force of gravity on 2. All right, so that is our diagrams there, right? And I don't know what the question is, but I do know that you have the force of tension in 2 different objects there, so that links them, right? Opposite or action-reaction forces there. And if we did the net force equation for each box, going back up here, right? AC goes towards the middle of the circle there. Box 2, so this would be AC this way. Here, this is in static equilibrium, it's just hanging there. So your V is 0. And so if we look at box 1, our net force in the x direction, because x is towards AC, is equal to MAC, which would just be FT based on our diagram. And then over here, our net force in the x direction is 0. And that'd be FG minus FT. So you have 2 equations for FT, and then you put in whatever values you need to put in, and you get the right answer.
Yeah, I didn't know it was simple. I guess I couldn't get the diagram correct.
It's not simple, but don't say it's simple. It's not simple. Obviously, if you didn't get it, it's not simple. That's a hard question, because that includes all 3 laws of motion in one question.
Isn't there like, oh no, that's y-axis, sorry. Yeah.
Okay, first law, because the mass number 2's in equilibrium, it's just hanging there, not moving up or down. It's the second law, because the box of the table is accelerating, right? It's going in uniform circular motion, which makes it Newton's second law of motion. And then as a third law, because there's 2 objects linked together by a common force.
If there wasn't like the surface and it was like our lab, what would be the first law?
It's still the same setup as your first law, just replace the table with a 2.
Okay.
Yep. Next question. As long as I've answered your question, Andre. Are you satisfied?
Yeah.
Okay. Sloan?
32 on page 101.
32 on page 101. A rope is pulling a block, calculate section. What's the rope doing? So the rope has a mass pulling a block with that mass. It's a great question. Which way is the rope pulling it? Is it pulling it up, down, left, or right? What do you think?
I think it's like horizontal.
That's right. So for that one, it's not a massless rope. And it's not moving. What's the answer? You know? Is it 31?
31.5.
The answer's 31.5, isn't it? Yeah. Yeah, because it's an action react. There's no map there, I don't think. Right? 'Cause it's an action reaction pair. So if it's pulling it with the force of 31.5 newtons, then the reaction force on the rope should be the same. Unless I'm missing something.
Yeah, it's just to calculate it.
Well, we could calculate it too, I guess.
When I calculated, I found mu, and then I just multiplied by mg, and I got the answer.
That sounds like a lot of work.
Yeah, but like, so there's actually,
So all I would do for that one, if it were me, right, you have, I'm getting from the question that you have a box with a rope that's attached to it, right? Not a massless rope like in every other question we've done. So what I think they want you to do is do like the free body diagram for the box and one for the rope. Your box would have your gravity, normal force, and tension going that way, right? And our velocity in this is 0. So I'll just make this way positive. And then the rope has your force of tension going that way. And this is what I don't get if it's on the ground. I'm gonna pretend my rope's on the ground. For whatever reason, my rope's on the ground, so it has a normal force which balances out the force of gravity, right? And 32 and it has an applied force, and then our applied force maybe 1.5 newtons. Right, so this is kind of what our setup is. So there's a force being applied to the rope's attached to the box has tension. So if we do this, if we're doing our calculation, our net force in the box in the x direction is 0. Just the force of tension. Yeah, that doesn't make sense. Yeah, well, I guess if it's not moving, there's gotta be friction.
Just want to see.
So at the end of the day, it's not moving. So it's not asking to find friction. Although that's what Andre did. Because there has to be friction there if the box isn't moving and there's an applied force to it. Right, so it doesn't say that. what they want you to recognize in the picture, and I'm not sure how that you would calculate it, would be that these are the actual reaction force here is the same. So if you were to like calculate it, you could go over here. If this is equal to 0, then you could say Ft minus, or Fa minus Ft is equal to 0. So you get Fa is equal to Ft. So your applied force is equal to the force of tension. And we know that these two are the same based on the third law of motion. So if you know the tension on one side, you're going to know the tension on the other side. Or you could just reason through it and know that the tension on the rope is the same on each side. So whatever the person pulls with is what has to come off the box as well. Right?
In real life, that doesn't really make sense though, because the box is moving, right? And if
No, it could have static friction on it to prevent it from moving.
Yeah, but it says it's moving.
Does it say it's moving?
Well, it says it's pulling a block, so a rope is pulling a block.
Yeah, the box is resting on a smooth horizontal surface. So is that I would take resting as in it's not moving. You would need more information if you had to figure out the acceleration or some other stuff. Right? If it was frictionless, then it's not resting. It would be accelerating. And then you wouldn't have this. So then you can find the A if you had to find the A as part B. Yep.
Could we do 55 on page 103?
Next page. Oh yeah, 55. I like 55. All right, so we look at 55. I'm just gonna erase this one.
Be a test question.
Sure. I just get test questions from textbooks. I just grab. I have like 5 different publishers of textbooks, and I just choose questions. I spread them out between like spicy, hot, mild.
I'm gonna give us like really hard diagrams to draw.
I don't know. My job is not to go out and make your life more stressful than it needs to be, but what you find hard might be easy to somebody else. So I can't really make any promises. All right, so there's a hammer hitting this nail, and there's a box, right? If we did our free body diagram of our block of wood here, Alright, so we did our block of wood there. What's our free body diagram look like for this block of wood? Hunter?
This is probably wrong. That's like, FS is going, where that's going. I said it was going up.
Yeah.
So,
Did you get the question right?
I got stuck on like the math. I couldn't figure out what to do. So no, I got it wrong.
Okay, so we have one FS going up. What else do we have?
Gravity going down.
Gravity going down, yeah. And there's 2 more, or 4 more forces here. Yeah, Jake?
There are 2 normal forces going opposite directions.
Yep, good. So this is, like say, Fn from the left side and Fn from the right side. What else? There's 2 more that need to go up there. Jake?
Another static friction going up.
Yeah, so we have static friction from the left side, we have static friction from the right side. And, Eric?
We have a force applied.
Yeah, we have force applied going downward. Alright, so we have all the forces here, right? So because it's trapped in a vise, right, we have two forces of static friction, one from each side. We have our applied force going down and force of gravity going up. Brennan?
Wouldn't there also be a force applied from both the left and right side as well?
That's the normal force, squishing it together.
Oh, okay.
Yeah. Yeah, it's a force perpendicular to the surface, yeah. Yeah. Alright, so we have a diagram that looks like this. Alright, it's in static equilibrium, so our velocity is 0. It's asking us what the what's it asking us again? The minimum normal force that each jaw of the vise exerts on the wood to hold each block in place. Alright, so we have, let's just say down is our positive x direction, just for fun. And this way is our positive y direction. Not that it matters. Alright. So what is our, so I know the net force in the x direction is 0 because it's not a motion. What is the equation, or net force equation here? Somebody who's not Andre, who's answering all the questions today. Jackson, what's our net force equation in the x direction?
Normal force on the left side.
Nope, x is
Oh, X is up.
X is not up either, nor is it left. Look at my compass. What does my compass say?
Oh, is it? Oh. So, force applied plus force of gravity minus the static friction.
Yeah, good. All right, so we have a net force equation that looks like this. And if we just expand this, we still have an FA, that doesn't change. We have an mg minus mu s f and left minus us f and right. Okay. So we have our two unknowns though, right? We don't know F and L, and we don't know F and R, but we know FA, we know MG, we have the mu values. Right? Under?
So would you just move on FA and MG to the other side and then factor? Or not?
Factor what?
Since you don't know. Oh,
You can't factor because they're different things.
Yeah, they're different. Yeah.
So how can we get it so we can factor it?
You can or can't?
Can't. What were you, Eric?
Let's solve for the y direction.
Yeah, solve for the y direction, right? Whenever we get stuck in one dimension, we gotta go to the other, because that's probably where our answer is gonna be. Alright, so if we go in the y direction here, right? This one's a bit easier. What's our net force equation look like for the y direction here? Ashley? Yeah, so Fn L minus Fn R. Alright, so whatever the normal force on the left side is equals the normal force on the right side. Alright, so we know that they're the same. Which we kind of guess in our picture anyways, because it's stationary. If one normal force is larger than the other, then it would be pushing it one way. Right, so they have to balance each other out. So I switched lanes here. I'm gonna go back over to this lane. So now I have FA plus MG minus US F and L minus US F and L is equal to 0. You can also switch you can do F and R as well. Doesn't really matter.
They're both the same.
So how do we get that F and L by itself? We want to get F and L is equal to something. Here it is. Right, we have two of them. How do we get it by itself? Any ideas? There's a couple of ways we can do this. Andre?
So you just move on FA and MD to the other side first? Or not?
Yeah, you could. I would not do that because I don't like negatives.
Okay.
How can you do that without getting negatives?
Do it. You gotta move the other side.
Yeah, move these guys to the other side, right?
Yeah.
So we have FA plus MG equal to F and L, get a US in there, plus. Yeah, so we move both the frictions to the other side. And then what can we do? Ashley? Before we get there, yes. So that's going to be 2 steps away. Pardon? Yeah. So what are you going to get when you put them together?
It's just two.
It's just 2 of them, right? These are the same thing. There's not even any factoring here. We just have 2 of them. All right, and then we do what Ashley said. We bring them US to their side. All right, we're gonna get our normal force, whatever that is, which is not what the question's asking. The question's asking for the force of static friction. Oh no, it is asking for the minimum normal force. So then, yeah, that should give you the answer. Let me know if it doesn't.
Wouldn't this just give you one of the normal forces, you know?
They're the same, right? We just proved it. They're the same.
Oh, okay.
If one's bigger than the other, it's going to accelerate in the direction of whatever one's bigger, right? So the net force wouldn't be 0 then.
Yeah, right.
All right. Next question. So again, the more questions you do, the better your process should be, right? You should be honing in a strategy that works for you. So I did mention before, and I'll tell you again, like when you guys are doing this, one thing you should be doing is writing down, like making like a step-by-step process that makes sense to you, right? A procedure, if you want to call that a recipe, right? So every time you see a force problem, you should know, like, here's my thought process. I'm going to do this first, then I'm going to do this, I'm going to do this, then I'm going to do this. Because no question is the same. And so you can't memorize a question or a way to get to a solution, but you can have